All right. Good morning, or whatever time you're watching this. We're going to talk about strong acids and bases today. This is going to be pretty easy, a pretty good lead-in. Once we start talking about weak acids and bases, that's when it gets a little more complicated. But this will be a lot of review. Okay. So, strong acids and strong bases are strong electrolytes. Now, we talked about this way back in Chapter 4. So a long time ago, when we were talking about precipitation reactions and oxidation reduction and all that stuff, we talked a little bit about acid-base reactions as well. Strong acids and strong bases completely split apart in water, okay? Which means when you put them into water, you put HCl into water, the H plus separates from the Cl minus pretty much every time, okay? They exist entirely as ions. The way the AP exam says it is they ionize excessively in water, okay, which is ridiculous to say it that way, but that's how they say it. So because of that, because you've got, you put HCl into water, you've got a bunch of ions, H plus and Cl minus ions running around in there, sort of. I'm lying to you a little bit, but we'll get to that in a second. But the point is, you've got ions running around in your solution, and because of that, you have a good current being able to be conducted, so it can conduct electricity. So hydrochloric acid is a good conductor of electricity. Hydrochloric acid in solution, I should say. So just bringing this back, because I'm sure that you've brushed up on this from time to time to make sure that you didn't forget it, right? Right. 7 strong acids you need to know. HCl, HBr, HI. I actually forgot HI was one, but it is. HNO3, HClO3, HClO4, and H2SO4. Alright, those are your strong acids, your most common ones. So, hydrochloric, hydrobromic, hydroiodic, those 3 are in the halogens column. Now you would think, based on that trend, that hydrofluoric, HF, would also be a strong acid. And I don't know if you guys have ever heard about hydrofluoric acid and what it does. It eats through glass. It's so reactive, okay? But reactive doesn't mean strong. And I don't remember if we talked about this earlier in the year or not. Did we talk about this? Difference between reactive and strong. Reactive just means, sodium is very reactive in water, right? Or pretty much with anything. Pure sodium, because it just wants to give away that one extra electron it has, that one valence electron it has, and so it will react with pretty much anything. That doesn't mean that it's a strong acid or a strong base. It's just reactive, right? Hydrofluoric acid is the same way. That fluorine ion will react with a lot of different things, okay? But hydrofluoric acid, HF, when you put that into water, most of the HF stays together, and only a little bit of it dissociates into ions. Okay, so that's what classifies it as weak or strong. So these 3 are strong, HF is weak. And then you've got, some that have polyatomic ions with them, the nitric acid, the chloric and perchloric acid, and then the sulfuric acid. Okay. So an example of strong acid in water. Now this is what I was talking about when I said, dissociates into H plus and Cl minus. Really, this is more technically correct as far as what happens. We talked about this a little bit either yesterday or the video before that. I can't remember. But what really happens here is this acid gives a hydrogen or gives a proton, however you want to say it, to this water molecule, and you end up with H3O plus. Okay, so that's really what's running around in that solution is not H plus by itself. It's the hydronium ion, H3O plus. It's water with 1 extra hydrogen. Okay, and then you've got your NO3 minus. Okay, which we don't really care about that much in that solution. It doesn't do a whole lot. So that's really the reaction of a strong acid with water. And really, it's not as much of a reaction as it just is. It's dissociating. Okay. But the H, you can also write this way, and either one of these ways would be considered technically correct by the AP exam. Okay, so if you'd rather write it this way, just HNO3 splits apart into H plus and an O3 minus, that's fine. Okay, but technically this top one is really what's happening. So why are we not using an equilibrium arrow on this particular reaction? Any ideas there? Well, okay, it makes sense. It's not an equilibrium, or it's not an equilibrium reaction if we're not using an equilibrium arrow. Why is it not an equilibrium? Okay, what's the definition of a strong acid? What defines something as a strong acid? Completely dissociates in water, okay? In order for it to go back this way, it would have to undissociate, right? Is it going to do that? No, because it's a strong acid, right? So it's not going to go back in the backwards direction, okay? So we write these reactions just with a forward arrow because that's really, it doesn't go back, all right? Strong acids do not undissociate, I guess is the best word I could think of, okay? They dissociate completely, they split apart, but they do not come back together, right? Oh, forgot this again, sorry. Oh, those of you who are watching the video, you already saw all the answers. Don't pay attention to it. Is it the only one? Oh no, here we go. Here's one more. Don't look. Okay, there we go. Where were we? Okay. So now we're going to practice calculating the pH of a solution with a monoprotic strong acid. What? Monoprotic? What do you think that means? One protic, right? Okay. What's a protic probably talking about? What does protic sound like? Yes, it does sound like produce. What else does it sound like that maybe has a little more to do with chemistry? Well, okay, products. Protons, that's what I was looking for, thank you. Alright, you need to go PROT, not PROD. You guys are thinking PROD. So, monoprotic means, one proton. Okay, in other words, it has one hydrogen that's going to dissociate when you put it in the water. Okay, 6 out of our 7 strong acids are monoprotic. Which one's not monoprotic? H2SO4, that's diprotic, right? Okay, so with all these other monoprotic strong acids, the ones that only have one hydrogen, this is a fairly simple calculation, okay? I'm going to have to show you, not today, I don't think. I think it'll be tomorrow, how to deal with the H2SO4, because it's a little bit different. So what's going to happen here, the H plus concentration is going to equal the original concentration of the acid, right? Because as we've talked about with things like sodium chloride, and I feel like I've prepared you pretty well for this concept, if you have a 0.1 molar solution of NaCl, then you can also say that it's 0.1 molar with respect to Na, and it's 0.1 molar with respect to Cl, okay? So it's just thinking about that ratio. So with all of the strong acids except for H2SO4, the H plus concentration is going to be the same as the original concentration of the acid. Okay? Because it completely dissociates and because it's just a 1-to-1 ratio there in the formula. So the pH of a 0.040 molar solution of HClO4. Okay, and honestly, this is not much different than what we were doing yesterday. The only difference is instead of telling you it's a 0.040 molar solution, the solution has a 0.040 molar concentration of H plus, I'm telling you it's a 0.040 molar solution of HClO4. But it's basically the same thing, right? Because what is the concentration of H plus in this solution? It's the same, right? Okay. So our H plus concentration here, because this is a strong acid, is 0.040 molar. Now, I'm just going to kind of help prepare you for something that's coming. If this was a weak acid, and I told you it was a 0.040 molar concentration of it, could I say that it had a 0.040 molar concentration of H+? Why not? Okay, some of that acid will dissociate, right? But not all of it. So if you have a 0.040 molar concentration of the acid, then you have less than a 0.040 molar concentration of the H+. Okay, and that's all we can say for now. In fact, that's all we can say until we know the equilibrium constant for that weak acid, okay, which we'll get to later. But for now, the H+ concentration is equal to the original concentration because we're talking about strong acids. So all you have to do here, pH is equal to what? Negative log of the H+ concentration, okay? So you take the negative log of 0.040, and that's going to give you your pH, which is 1.4. Which actually brings up something that I forgot to mention yesterday. And I'm going to have to look again. I'm not as strong on the mathematic part of the logs. But for some reason, you lose a significant figure when you do pH. Okay? And so, technically, this is probably one more sig fig than I should have here because we only had 2 sig figs in our concentration. But you know, as long as you're within 1, you're okay. So that's never going to kill you when you're doing your pH problems. But all right, hang on just one second. Okay, sorry about that. All right, so then second sample problem here. An aqueous solution of HNO3 has a pH of 2.34. What's the concentration of the acid? Not the concentration of H+, what's the concentration of the acid? You're going to 10 it, right? Okay. So remember, to go from pH to H+ concentration, you just take 10 to the negative 2.34, okay? And just in case we need a little refresher on why that's the case, if pH is the negative log of the H+ concentration, then if I have the pH, the way that I'm going to solve for H+, I'm going to take the negative over to the other side. So negative pH equals just the log of the H+ concentration, right? I don't have enough room here. So then 10 to the negative pH is going to equal the H+ concentration, okay? When you 10 both sides, you get rid of the log. So 10 to the negative 2.34 is giving me a concentration of about 0.0046 molar. So 0.0046 molar, that's the concentration of H+. What's the concentration of the acid? It's going to be the same. Good. Because HNO3, when that dissociates, it dissociates in a 1-to-1 ratio, right? There's only one H+ there. And it always dissociates because it's a strong acid. So this is going to be equal to our concentration of the acid itself. Okay? So 0.0046 is our answer here. All right, strong bases. The strong bases are pretty easy to remember. They just have hydroxide at the end, OH. Okay? Not all things that end in OH are strong bases because some of the things that end in OH are not very soluble in water. Okay? But the ones that are soluble in water, I mean, sodium hydroxide and potassium hydroxide are the most common ones. Hydroxides of any alkali metals are going to be strong bases, but lithium hydroxide, rubidium hydroxide, and cesium hydroxide, we just don't use them very much in lab settings. Okay, it's usually sodium hydroxide and potassium hydroxide. So the other ones, the other alkali metals technically are strong bases as well when connected with hydroxide. But sodium hydroxide and potassium hydroxide are the main ones you need to know. And then of the heavy alkaline earth metals, calcium hydroxide and down on the periodic table. Okay, beryllium and magnesium hydroxide are not very soluble in water, so that's why those two are not considered strong bases. All right. Alkaline earth metal bases have limited solubilities, however. Okay, that's what we just talked about. So honestly, probably the best strong bases to use would be sodium hydroxide and potassium hydroxide. Okay, because those are going to be very soluble in water. Because as we hopefully remember from our solubility unit, alkali metals never precipitate with anything, right? Okay, so there's a couple other ways to make strong basic solutions. If you have O2 minus, H minus, which is awkward, and N3 minus anions, okay? None of those like being having that kind of negative charge necessarily. To some extent they do, because they have, full octets with that arrangement, or, hydrogen has a full duet here. But they're very negative, okay, which means that they are, and the more negative they are, the more easily they can attract something that's a little bit positively charged, like a hydrogen on a water molecule, okay? And so what's going to happen here, if you've got O2 minus, okay, so you've got something that's very negatively charged coming into contact with a water molecule, and the water, again, we talked about this, water is very polar, so it's got a partial negative charge here and a partial positive on each of the hydrogens. Well, these positively charged hydrogens, or partially positively charged hydrogens, are very attracted to the negative charge on this O2 minus, right? So then what's going to happen here with this O2 minus is that it ends up attracting one of these hydrogens, and then you end up with OH minus and OH minus, right? So OH minus and OH minus, and that's why there's two OH minuses on this side. On the H minus here, again, it's negatively charged, so it's attracting a hydrogen, so you're going to end up with H2 gas there. You're going to have a little bubbling happening in that reaction. You're not going to see this reaction in our lab because H minus is kind of a rare anion to have. But you would have H2 gas, and then you would make OH minus, okay? And then the N3 minus here, and that's going to pull hydrogen off of the water. Actually, it would pull a hydrogen off of 3 waters to form NH3, okay? And then you'd end up with 3 OH minus ions. So any of these would be considered strong bases as well, just because they're able to pull a hydrogen off of water pretty much every time, okay? So those are some good ones to remember. You won't see those probably as much, but you might see them. By the way, even NH3 is considered a base. It's not a strong base, it's a weak base. But NH3 is even capable of pulling another hydrogen off of a water, making NH4+. Okay, so you can imagine N3 minus is a very strong base. If even after it's taken 3 hydrogens, it still can take 1 more. Okay. All right. Calculating the pH of a basic solution is easy. You just need to be careful. Because it's not always a one-to-one stoichiometry with the bases, since we've got some alkaline earth metals in there as well. Okay, so pH of a 0.028 molar solution of NaOH. Well, what would be our strategy on this one? Okay, negative log of this concentration. Okay, so if we take the negative log of this concentration, is that concentration the same as our OH minus concentration? On this one it is, right? Because it's a one-to-one ratio here between the sodium and the hydroxide, okay? So 0.028 is actually the OH minus concentration as well. So then if we take the negative log of that, it's going to give us 1.55. Number seems a bit low for a basic solution, doesn't it? Okay, we found the POH just then, didn't we? Okay, this is not, you got to be careful with this. This is not the pH, this is the POH, right? Because we took the negative log of the hydroxide concentration. So then you have to take 14 minus that number, and that's going to give you your actual pH, which is going to be about 12.4. Okay, so that's another thing you need to watch out for with the bases. Okay, if you take the negative log of the OH minus concentration, that's going to give you your POH, and then you have to subtract that from 14. If they're asking for the pH. Now, if they're asking for the POH, then we would have been fine. Okay, now for B, we've got a 0.0011 molar solution of CaOH2. What's the trick on this one? Okay, there's two OH minuses there, so as soon as you put that into water, it's going to dissociate, and you're going to have twice as many moles of OH minus as you did of the whole thing. Okay, so our concentration of OH minus here on letter B is going to be 0.0022. Almost used my calculator for that. Okay, and then again, we'll just do the same process now. Take the negative log of that number. It's going to give you 2.66 or so. So the POH equals 2.66. Okay, which means the pH would equal 11.34. Okay, and on that one, probably want to be careful not to use too many sig figs here. It's going to be 11 point. No, actually, I think that's right. You know, I take back what I said before. I'm going to figure this out for class, so don't let my sig fig thing mess with you on the pH. I need to look that up, but I think actually what it might be is it's the numbers after the decimal that matter for the pH. Okay, so if you've got 2 sig figs in your number, then you'd want 2 decimals in your pH. But I'll look that up to make sure. Okay, so I'll let you know on that one in class. All right, that's it. So pretty quick one today. Tomorrow we'll make up for it. Yeah, sorry. All right, I'll see you guys in